Ciao, and welcome to the Frontier Space Podcast, a dialogue about how space technology and exploration are transforming our solar system. Dr. Barth, welcome to the Frontier Space Podcast.
Thank you. It's good to be here.
We're delighted to, finally touch base with you and have you here today. And whereabouts are you calling in from?
I'm from the University of Toronto, so I'm calling from University of Toronto.
I remember reading about SuperBIT and the missions several months ago. We'd love to hear more about this balloon-borne SuperBIT telescope you and your team are pioneering.
Yeah, sure. What would you like to know? Should I just give you an overview of what the whole story is?
Yeah, something like that.
Sure. I do astrophysics experiments where we're trying to look at, stuff in space. And if you're trying to look at stuff in space from the ground, you're obviously looking through the atmosphere. And the atmosphere can be a challenge for imaging. In some wavelengths or some colors of light, including colors of light your eyes can't see, the atmosphere just straight up absorbs all the light coming through it. So like in the far infrared, the atmosphere is basically opaque. You can't see anything. At some wavelengths, the atmosphere doesn't so much absorb the light, although it does somewhat, but it will also distort it, where the light gets bent by temperature and pressure gradients in the atmosphere. I don't know if you've ever seen a mirage, hot air coming off a road and the person in the distance is all kind of wobbly. Like they like to do those in some cool movie shots, right? So that mirage thing going on, you see, you know what I'm talking about, right?
Yes.
Yeah. So the same thing happens when you look straight up at a star. You just can't see it with your naked eye very well. Well, you can a little bit. You see those stars kind of twinkle. But when you look at a star through a telescope, you see this mirage effect happening, and the image is just dancing around, which makes it really hard to take high resolution images of anything in space from the ground. So the solution to both of these problems, working in the far infrared where the atmosphere absorbs the light, or working in visible where the atmosphere distorts the light, is to get out of the atmosphere. The obvious way to do that, obvious-ish, is to build a satellite. So you have something like the Hubble Space Telescope, which operates in orbit. There's no air, so there's none of this distortion happening. So you can get a much higher resolution image. The resolution of a telescope in space is limited by the quality of the optics and the size of the telescope. So Hubble is a 2.5 meter telescope. It can make very high resolution images. So less than, we would say less than 100 milliarc seconds, which is an interesting unit. How do we do this? You have, what a degree is, a degree of angle. There's, 90 degrees is like that. You can't see my hands because we're not on video. The moon is about a half a degree on the sky. So that's how big the moon is, about a half degree to your eyes. Okay, then a fraction of a degree, the units we use is a arc minute. So there's 60 arc minutes in a degree. One arc minute is about the resolution of your eyes. And then you can divide arc minutes down into arc seconds. There's 60 arc seconds in an arc minute. One arc second is about the highest resolution you can get from the ground. You can get a little bit better than that, but that's kind of a good rule of thumb. A good telescope on a good site on a good night, maybe you can get 1 arc second resolution. And then, so Hubble Space Telescope can get less than 0.1 arc seconds resolution. So very, very, very high resolution. That's because it's in orbit. Now, obviously, putting a spacecraft in orbit is really, really expensive. And so it might be nice to be able to get something out of the atmosphere, but not in orbit. So it turns out that they've developed these high altitude stratospheric balloons. So these are balloons that are, when they're fully inflated, maybe between 10 and 40 million cubic feet of volume. So sort of like maybe the balloon, when it's fully inflated, might be something in the order of 100 meters in diameter. These are enormous balloons. And they can take a payload of up to maybe 4 tons to an altitude of 35 or 40 kilometers. And that is that's above 99.5% of the atmosphere. So the effect of the atmosphere is 200 times less than it is on the ground on order. And for visible light imaging, that gets you to the point where the atmosphere just doesn't matter in terms for your telescope's ability to take high resolution pictures. So for being on a balloon can be almost as good as being on a satellite, but a lot cheaper, which is great. Now, the downside of being on a balloon is that you only have a flight for as long as the balloon flies. You can't fly a balloon for decades. So the way that NASA managed to get flights for more than a day for many decades was to launch from Antarctica. So I've done a number of launches from Antarctica. In Antarctica, in the austral summer, so maybe in December, there's no sunset. And so you launch the balloon and it can just stay up for days and weeks. The longest flight from Antarctica was something like 50 days, 56 days, something like that. So you can fly very long flights from Antarctica in the austral summer where it's constant daylight. The problem there, and that's great for like a millimeter experiment, like Boomerang, experiment we did back in the late 90s, or like BLAST, a submillimeter experiment looking at star formation that we flew up in, like the most recent flight was just a few years ago. These can stay up for weeks, and the fact that there's daylight doesn't really matter because as long as you're not looking at the sun, your telescope, the atmosphere isn't scattering millimeter or submillimeter light. And so it's fine. But if you want to do visible light or near ultraviolet light, you can't do it in the daytime because the atmosphere is scattering too much sunlight. So you need nights. So the question is, how do you go about flying for weeks an experiment that needs to operate at night? So the trick comes down to that point where I mentioned the sun rises and shines in the balloon and the gas in the balloon expands and you have to vent it out the bottom. Well, it's been about 20 years. NASA has been working on building what's called a super pressure balloon, a balloon where they can keep that valve closed through sunrise and the balloon becomes overpressured but doesn't pop. And they've had, out of 3 major test flights where they have day-night cycles, the longest flight of those test flights was 45 days, one was 35 days, which is pretty good. Their goal, of course, is to get up to months. And so we've been once it looked like NASA was actually going to manage to get these super pressure balloon flights working, where you actually have the ability to fly days and weeks, we decided it made a lot of sense to try and build a visible light telescope. So we've been working on SuperBIT, which is basically a visible light telescope that can fly on a balloon above all the atmosphere, so you get that diffraction limited, extremely high resolution imaging. But because it's on a super pressure balloon, you can fly for weeks or hopefully months. So that's the basic idea. Now, SuperBIT, originally BIT stood for Balloon-borne Imaging Testbed. We wanted to learn how to do it because, well, people hadn't been trying to do it because there wasn't much point. We only had one night. SuperBIT by itself is not as good as Hubble. Hubble's better, it's bigger. We're a 0.5 meter telescope. Hubble's a 2.5 meter telescope. I mean, camera technology has come a long way. So we have a 69 megapixel camera with extremely low read noise and very good quantum efficiency and very low dark current. Those are all terms that tell you it's a great camera. So our camera is much better than what's flown on Hubble. But nonetheless, our mirror is so much smaller. We end up being interesting with respect to Hubble, but not better than Hubble by really close. It's a pretty great experiment. But its real purpose is to develop a next generation experiment, which will be a 1.5 meter telescope with an even better camera. And we expect gigabit, which we're calling it, unless you want to donate money to it, then we can call it whatever you want. The gigabit should be, 50 times more sensitive than Hubble, or just 50 times better light gathering capability at a very similar resolution to what Hubble can do. So that's our medium-term goal. So we've gotten SuperBIT working. We were able to demonstrate that yes, we can get 0.25 arc-second imaging from a balloon. We want to go to another factor of 3 better with gigabit. And so now we're going to try and actually do one of these superpressure balloon flights with NASA to demonstrate the whole thing and actually try and learn a whole pile about this distribution of dark matter in galaxy clusters as a really awesome outcome of a test flight, which actually is testing something that's so awesome that's actually meaning a great science flight. So there's kind of my story. In one big monologue.
Yes. Lots to take in.
Yeah, so you can go back and bounce me off anything you want me to cover again, for sure.
Okay. So for some clarity,
Yeah.
So you flew at 40-kilometer altitude with
35 to 40. It depends on the balloon and the payload. The superpressure balloons are a bit lower. They're more toward the 30 to 35 kilometer altitude. The balloons are stronger and therefore they're a bit heavier, so they can't go quite as high. But it's pretty good. But it's still like plenty high enough for the visible light telescopes to not care.
Okay. Yes. And the balloon was the size of a football stadium and
football field, not the stadium itself. It's about 100 meters.
Okay.
Yeah.
Nice.
Stadium's awfully big. 100 meters is awfully big, but
and the SuperBIT was capable of flying a payload mass of 1 ton, 1,000 kilograms.
Yeah, SuperBIT is a 1-ton payload. The heaviest thing we flew was Spider in 2015 from Antarctica, and the pin weight there was close to 4 tons, which is like unbelievably heavy. It's a monster.
Wow.
And that's a big balloon. That balloon was 34 million cubic feet.
But the telescope was only 80 kilograms?
The telescope itself, SuperBIT, it's something like 80 kilograms for the actual, it's a carbon fiber mount with a glass mirror made by an Italian company called Officina Stellari. So it's got the beautiful Italian feel to it, It's like, Ferraris and telescopes, both, look very shiny. Very stylish carbon fiber, until we get a hold of it and glue heaters and thermometers all over it to temperature stabilize it, and then it looks sciencey again. But then there's everything else going along with it. There's the computers and the tracking cameras and the science camera and the batteries and the elevation motor and the azimuth motors and the roll motors and the image stabilizers and the solar panels. And pretty soon you're moving up to around about 800 kilograms for our stuff. And then you need to add the NASA communication box, and you need to add their solar panels and the antennas and the antenna booms and the cage to protect NASA's electronics. And by time you're all done, you're up to a couple of tons. And so it's like you just keep adding things and it gets heavier.
Yes. It sounds like we would have a working payload. We could put, like, I don't know, 1 ton to 2 tons of any kind of payload into the stratosphere.
Oh yeah, absolutely. And stay up there for months.
Yes.
On a superpressure balloon, or weeks on a zero pressure balloon over Antarctica, or overnight for a conventional flight from mid latitudes. We fly test flights out of Timmins, Ontario, which is a pretty great place because there's very few people outside of Timmins, near Timmins. It's just all surrounded by forest. So we've had a few test flights out of there where you test something overnight. That's where we verified that SuperBIT actually can do what we want it to do. So now it's down to launch from New Zealand.
In March, I recall.
Well, that was the hope. Now, there's all sorts of stuff making it a bit of a challenge. COVID has made travel to New Zealand dicey. U.S. government vaccine restrictions may have an impact on who from the launch team is willing to go. Yeah, so I don't know if we're going to make it this March. It may be a year March. It's still kind of up in the air, but I'm feeling kind of pessimistic about it today. We'll see.
There's SuperBIT in 2022 and Gigabit in 23.
Well, that was the hope, but it might be SuperBIT in 2023,
Okay.
and try and slip a test flight for Gigabit in before. Now, Gigabit won't be flown with a science instrument probably before 2029. It's going to take a while to get this working. It's an incredibly difficult challenge. Where SuperBIT is trying to do a quarter of an arc second. We're kind of like 4 times better than a typical good telescope on the ground. Gigabit's trying to do a factor of 3 even better than that. So the level of image stability required is like pretty horrifying in terms of how hard it is. So I expect it's going to take a little while to get, for example, the telescope. A lightweight telescope of that capacity built is going to be hard. Right. So this is, one of the highest resolution telescopes ever made. Almost never in the history of telescopes has there been one that needed to have this high quality optics. HST was one of them. Euclid is another one, which will need this level of quality. But it's not as if there's a lot of experience by anybody making telescopes this good. Because when you're building a telescope on the ground, the atmosphere is going to limit you to an arc second anyway. So there's you have a little bit more wiggle room in being not quite perfect before you'd really care.
And haven't read up on the impact that SuperBIT and these balloon-borne telescopes will have on the backlog of these imagery requests for Hubble.
Yeah. So Gigabit, which is really what we're chasing after. That's the thing that we're really excited about. Gigabit should be able to, 1 gigabit flight should kind of be able to collect the same number of photons and the same amount of, light, some combination of picture area and pixel depth and picture resolution as Hubble could do in 10 years. So yes, it should be able to do a lot toward reducing the backlog of imaging requests. So it's really, really exciting. Of course, there's 2 other really exciting satellites coming out in the next little while. There's Euclid and Roman, which are two space satellites, space telescopes. Gigabit's imaging speed is kind of not much different than theirs. I mean, they're a lot different than each other. Gigabit will be faster than Euclid and slower than Roman. But the big difference is that Roman and Euclid both observe in the red and the near infrared wavelengths, and Gigabit focuses on going into the blue and the near UV. So there, even there's no other instrument currently operating or planned to operate in Gigabit's bands, which gives it a bit of a niche, which is nice. And it's got a similar imaging speed to those two satellites, kind of in between them. So you could argue that, well, the reason that nobody does blue and near UV is because it's not as interesting. It's like, well, we'll find out. It looks at different things. It's looking at things at moderate, not high redshift, it's looking at things that are hotter than you would with those other instruments. So it's kind of different science goals.
And Gigabit is also focusing on imaging the dark matter distribution, and
it'll certainly be amazing at that, but it's going to be a much more of a flexible instrument than that. We can also go after, looking at stellar populations and globular clusters, going after looking for, trying to find black holes in globular clusters, trying to go off and look for some of the missing baryons by looking for the glow around galaxies from redshifted Lyman alpha. There's a very wide range of other science that Gigabit will be capable of doing beyond the dark matter. Obviously, we're really excited about the dark matter lensing studies, but it's also true that Euclid and Roman will both be going after that science and be doing a really excellent job of it as well. So
awesome. Also wanted to revisit the cost savings we briefly discussed about. So SuperBIT was developed for $5 million US.
Something like that, yeah. I mean, depends on how you count it, and some of that was development and learning how to build balloon-borne telescopes, and then some of that was building SuperBIT. So, but if you kind of wrap up the whole thing, maybe 5 million is not a bad number, which is obviously a lot less expensive than a $1 billion satellite mission, or a $6 billion satellite mission, or a $10 billion satellite mission. On the other hand, it produces a lot less data. It flies for a lot shorter. Right, so Euclid Space Telescope costs a lot more, but it flies for a lot longer. And so the cost per flight is far, far less. The cost per hour, it's a harder case to make that either one is particularly dominant over the other. The big advantage then is with the balloons is that you can try new things, you can try new instruments, and you can have your graduate students and undergraduate students actually work on building it, which isn't going to happen with a $6 billion mission. So is that extra, we get to be involved. You get to be involved with competitive science. It's not, when you include the total costs, when you include the total mission length, lifetimes, balloons and satellites have traditionally been close, but the incremental cost for a balloon is far, far less and allows you to try new and different things and try and do things that maybe aren't worth a $6 billion mission, but are definitely worth a few $1 million.
Yes, and so Hubble cost $6.5 billion from U.S. taxpayers. Colin,
sure. I haven't looked at how much Hubble cost lately, so I'll take your word for it.
Yeah, I think that's around 1,300 times cheaper with SuperBIT.
Yeah, that's right. But also, Hubble has been flying now since 1990. So,
yeah.
Yes. And so that's, you have to take that into account. So I'm certainly not feeling, I don't believe that the days of satellites are even close to over. In fact, I think that with the decreasing costs of launches, we're going to see new and better and more amazing things being done on satellites as the costs there come down. So I think there's definitely room for both technologies, depending on what you're trying to do. The great thing about the satellite, the balloons, is the ability to bite off a smaller bite and get less time for a lot less money, and do something where you can iterate until it works. You can involve graduate students and undergraduates in the development process, those are a lot of the really huge advantages. So, and obviously, camera technology has come a long way. So the fact that we can build a gigabit, which is much better than Hubble, 30 years later, well, okay, it's also 30 years later. So that's not surprising. We're not vastly better in, dollars per image.
Yes, but I think it does put things into perspective in that this balloon operations in the stratosphere is game changing.
It is, because you can try new things. Somebody can say, hey, I've got this new instrument, I've got this new UV spectrometer I want to put on a satellite. It's not worth $1 billion to put on a satellite, but a balloon flight, I can answer some really exciting science questions and then go on to something different next year. And that's kind of the vision I have, is where you can do optimized experiments on a much higher cadence once you get this technology working, and try different things where it doesn't make sense to build a $6 billion satellite and fly it for a decade. A $6 million instrument for a couple of months is all you really need. And it's absolutely the right technology there, incomparably the right technology. So that's where the ballooning just is incomparable in that sense, where you can try something innovative and different, where a whole $6 billion mission doesn't make sense.
You start to wonder about all sorts of ways and methods that we could increase the lifespan of these stratospheric balloons. And wonder if we could put some kind of propulsion element or
yeah, so
or like you mine the atmosphere or something for extended lifespan.
Yeah, that's interesting.
Yeah.
So one of the big one of the ultimate lifetime limitations right now of one of these missions, if they get the balloons really working really well, a likely lifetime limiter will be if the balloon is about to fly over a very large population center, and the safety people become concerned that the likelihood of it not falling out of the sky while it's over a city isn't high enough, because you don't want to drop a 2-ton payload on somebody's car. And so they did do a bunch of research maybe 15 years ago into whether or not they could put propulsion on a balloon, and in order to keep it from flying over Sao Paulo or something. Right now, what they have to do is if the balloon is heading for Sao Paulo, then they're going to drop it in the ocean before it gets there, so it doesn't. So they looked into it, and it doesn't look like propulsion at those altitudes is really practical, because the pressure is so incredibly low that it becomes extremely difficult to change the trajectory of the balloon. The balloon's going to go with the atmosphere, it's going to go with the wind. Pretty much that's what's going to happen. So I'm not super optimistic they're going to make that work. They haven't been. I think the early studies made it seem like it was going to be more of a challenge than was likely to work. Although that, there may be new ideas come along, then it might come back. At this point, I don't think that's being pursued, unfortunately. What's interesting was when you fly one of these super pressure flights over the southern hemisphere, it just goes wherever the wind blows. And the wind it might be going east, and it might go west, it might go north, it might go south, it might sit over the ocean for a week because it's got into some sort of low wind speed region. It might take off going really fast. It's really interesting. Look at some of the trajectories from these previous flights. It just kind of wanders around in a kind of a fun way.
Start to wonder about all the coatings that could be applied to the exterior structure of the balloon.
Trying to use radiation pressure to drive the balloon. Yeah, radiation pressure compared to the wind speed, the force of wind, is extremely small. So I don't expect that would be particularly productive. Like on a satellite where you're traveling for years and you have no other forces acting on you except for gravity, then that actually can start to become interesting. But I think on a balloon in the wind, it's going to be not super likely in a matter of days that you can get enough trajectory change out of radiation pressure. They thought about using wind shear. Basically, the idea is that as you change elevation, the wind speeds can be different. So maybe you might want to try and drop a sail down to a lower altitude where the wind speeds are different, and use that to try and change the trajectory of the whole thing. I don't think that ends up being very, very heavy and complicated and maybe not work that well. They tried trying to use, they looked into using very, very large propellers, but they have to be so large. And all of these would just wreak havoc on our pointing system, like trying to precision point the payload while it's being yanked around with one of these systems would be kind of entertaining. So that being said, if you need more than a few months, you probably should be thinking about a satellite. That's kind of how it is.
Yes. So you primarily invested in this for research purposes, or are there any commercial ambitions?
Well, it's a combination of research and pedagogy. It's a really great way of getting experience if you're a grad student or a postdoc or even an undergraduate on building a whole system from design to a mission, and not really being locked out of any level of it because the entire thing is. And so I really, really like that. And the students that I've had have been able, come out with a pretty broad set of knowledge on how to build an entire system, from mechanical engineering to software to science analysis. So I like that aspect a lot, the educational point of view. And then of course the research potential is enormous. There's a few of my former grad students who've formed a company here in Toronto to produce payloads for other groups. It's taken a long time to really learn how to do this right. And so if you have a research group who has a great idea for an instrument, and they're really good at detectors or at telescopes or something, but they don't have the expertise for building balloon-borne gondolas and power systems and communication and control and thermal analysis and all those things that go into actually making the payload work. The idea there is that, hey, you can just go ahead and contract with these guys and they'll build you your gondola and pointing system, and you can focus on what you're good at. And that seems to be going pretty well. They've got a few customers and quite a bit of interest in it to just sort of, again, make this technology more widely available to people. And I think that's a lot of what I'm excited about going forward, is to getting it to where as many people as possible can benefit from the flexibility of these instruments, and also to really start dropping the development time. So we're not spending our entire time learning how to do something and then doing it, but to have that expertise kind of be stable so that we can provide the payload to anybody with a good idea.
Curious, could we point some balloons to closer in the solar system, and collect spatial resolution of the moon, Mars, and other
absolutely
bodies?
So I assume you've looked at HST images of the planets. HST can do a pretty good job in imaging Jupiter or Saturn. And similarly, gigabit could image Jupiter and Saturn. Now, the thing about gigabit is its huge advantage is the extremely large field of view. So in a sense, imaging Jupiter would be kind of sad to be wasting your instrument in that sense. You can do what's called lucky imaging from the ground and get a long way toward doing very good imaging of the bright planets, even from the ground, where you don't need the large field of view. So yes, gigabit would be very good at imaging the planets. We can map out Jupiter weather for however long it's not below the horizon without ever having to worry about the Earth's weather in the way. It might not be the most cost-effective way of doing it, but you certainly could. It'd be amazing at it.
Yes. I had two more questions here.
Go.
The first one being, with SuperBIT and gigabit, could we image the atmospheres and surfaces of exoplanets?
Okay, so these telescopes have basically a very similar resolution to what HST already has, right? So we're not getting better than HST in resolution. HST is still kind of the benchmark for high resolution imaging. HST has imaged some, large extrasolar planets in like protoplanetary disks and things like this. For that stuff, you generally, so far, they've wanted to operate in the infrared, where you're looking at the glow from the hot object rather than from looking at reflection off sunlight. Or you can do both. So gigabit, HST, not really high enough resolution to like image it as more than a dot in very special conditions like very large planets. So like the idea of a terrestrial planet imager requires a very large and extremely good telescope with the ability to really, really strongly block out the light from the star. And actually, maybe the hardest part about it is getting that contrast, because you're looking for a dim little planet next to a really, really bright star. So you need what's called a chronograph to be able to block out the light from the star in order to see the planet. And that's hard. These instruments are not really designed for that. One could do it. There's been discussion of balloon-borne chronograph telescopes, which is possible. I think that for doing a chronograph, actually imaging the surface of the planet, you're probably better off stringing for a satellite, because you get much better control of thermal and vibration and things like that. On the other hand, looking for infrared emission from a hot planet close to the sun, close to the star, that's something you can do from a balloon. In fact, we're involved now with a project called Excite, which is basically taking SuperBIT, replacing the visible near UV camera with a mid-infrared camera, and looking for the emission from hot Jupiter mass planets orbiting very, very close to the central stars, and looking at how the emission changes as it orbits the sun or the star, and from that, learning about the spectrum of their atmosphere and therefore the atmospheric contents. So that's something that we can do, and in fact we're currently involved with doing. And that's a few years out before those come forward. So yeah, planet work from a balloon is possible. You need to make sure you're kind of doing the right project.
Very exciting. Yes.
Yeah, it is. There's so much going on right now in science, and in technology is opening up these things. It's exciting. It's really fun.
Yes. And the impact of miniaturization and might improve everything all around 10, 20, 30 years from now.
Yeah, we can't make the apertures smaller because just the physics of light. If you want a high resolution, you need a large aperture, a large telescope, a large mirror. But everything else can become increasingly light. And even with the balloons, if we really needed to, we could have the rest of the payload be a lot lighter if we're willing to spend the money and the effort. So we just haven't, because there hasn't been a huge motivation. Like when you're flying a payload, it's like, okay, your mass budget is 800 kilograms. There's no real motivation to spend the money to make it 200 kilograms.
Yes.
But if we were to put it on a satellite and had a 250 kilogram budget, then you bet we would immediately think of lots of ways to make it lighter.
Yes. Awesome. Well, really appreciate your time today, Barth.
Yeah, it's been fun. Have a lovely rest of the day. And let's explore the universe.
Yeah, yes. Arash, look forward to, hopefully watching the SuperBIT and Gigabit documentary sometime.
Okay. Well, we probably should start recording some footage for it then, if that's going to happen. So
look forward to watching.
All right.
All right.
Have a great week. See ya.
See ya.
Bye.